Okay, in this tutorial we're looking at section 8.4, which is on applications, and to start off we're talking about our areas between curves. Okay, so this is one of our dead set all-time favourite applications. It's something that's going to come up at some stage on a SAC or one of the exams, guarantee it, lock it in. Okay, so the idea is to finding our area between two curves as we've got shown there. Okay, so if we just ignore this part for a second, okay, what we're looking at is finding the area from A to C, okay, between our curves. Okay, to do that, okay, we go the integral from A to C of g of x minus f of x dx. Okay, and really what that means is we're finding the area under g of x, which would be all of this area, and then we're finding the area under f of x, which is all this area, and taking it away. Okay, the thing to note, and that's why I've done this example here, is if our two graphs cross, okay, at some point, then what we need to do is split our overall region into smaller regions. So in this example, A to C and C to B. Okay, and it's always the equation that's on top, okay, first minus the equation on the bottom. Okay, so you see here g of x is on top of f of x, but here f of x is on top of g of x, so it's f of x minus g of x. Okay, so as I said, here always the function on top is first. Okay, this still works if the area between the curves is below the x-axis, so if we're down here it still works. And in fact it also works if we have something like this. Okay, this might be g of x, okay, and this is our f of x, okay, and we might be finding this area here. Okay, it still works all the time. Okay, we don't have any issues there. Okay, the next bit we look at is the average or mean value of a function, and it's found by 1 minus b take a times the integral of a to b of f of x dx. So if we want the average or mean value of a function, it's just a little thing that we have in there. Okay, it's often easy to overlook it, but again, I'd almost guarantee that there's going to be an average value question on one of the exams. Okay, the last part that we talk about in this section on application is kinematics. That's talking about our displacement, our velocity, and our acceleration. So if we have a function for our displacement, well, if we differentiate that function, we're going to get a function for velocity, and if we differentiate our function for velocity, we're going to get acceleration. Which means, if we go back the other way, we've got a function for acceleration, and we integrate it, we'll get a function for velocity. If we integrate that, we get a function for our displacement as well. Okay, so we'll get stuck into looking at some worked examples. Okay, so the first one that we're looking at is worked example 6. Okay, and we've got the functions f goes from r to r. Okay, and it's f of x equals x plus 2 minus x. Okay, and we also have the function g, which goes from r to r, okay, g of x equals x plus 2. And they give us the graphs of those. So what it looks like is, let's say we've got something like this, and we look like this, and they tell us that, well, this is the point M0, this is the point PQ, okay, this is our y equals f of x, and this is our y equals g of x. Okay, so that's what they tell us. Okay, and they tell us that the graphs intersect at M0 and PQ. Find the values of the constants M, P, and Q. Okay, well, we know simply here that where they intersect here is one of our x-intercepts. Okay, so what we do is let y equals 0. Okay, rearrange g of x, and we're going to get that m equals -2. Okay, that one's pretty straightforward. Okay, and what we need to do then is we also need to solve these as well for our other point. Okay, so what we need to do is set our equations equal to each other, okay, and say that we've got x plus 2 equals x plus 2, 2 minus x. Okay, easiest way to do this is divide by x plus 2. So yeah, x plus 2 divided by x plus 2 gives us 1. equals 2 minus x. Okay, if we add on x and take away 1, we get that x equals 1. Okay, so that means our p-value is equal to 1. Okay, we sub in our p-value, okay, of 1, or our x-value of 1 into this equation, and we're going to get that q, okay, is equal to 3. Okay, so that's the first part of the question. Okay, now we need to find the area bounded by the two curves. So we're trying to find this area here. Okay, so we needed these points. Okay, so we had our terminals. Okay, so we know we need to integrate now from our lower value, which is minus 2, okay, up to our upper value, which is 1. Okay, our function that's on top is f of x. Okay, and f of x is our x plus 2 minus x. Okay, and then we've got to minus our x plus 2 dx. Okay, so what we need to do is we need to expand these brackets, and we integrate from minus 2 to 1. Okay, we're going to get 2x, okay, take x squared, okay, plus 4, okay, take 2x, okay, minus x minus 2 dx. We simplify that, we've got minus 2 to 1. Well, we've got minus x squared plus 4, okay, and then our 2x and our 2x cancel out. Okay, we've got to take away an x, and we've got to take away 2. I should have just done that in the one step. So we're going to integrate from minus 2 to 1 of our negative x squared minus x plus 2, okay, in terms of x. Okay, so when we do that, we're going to get, well, it's going to be negative x cubed on 3 minus x squared on 2 plus 2x. Okay, from minus 2 to 1. Okay, when we sub in our values, then we've got negative 1 on 2, take 1 on 2 plus 2 minus, it's going to be negative, it'd be negative 2 cubed is negative 8 times negative 1 gives us positive 8 on 3. Minus 2 squared is 4, so it'll be minus 4 on 2, so minus 4. Okay, so when we do that, okay, simplify our two brackets, bring everything together, what we end up is 4.5 square units. Okay, so that's worked example 6. Okay, there is a worked example 7 if you want to have a look at that one as well. It's along similar lines, so I'm just having a look at worked example 8. Okay, so we want to find the average value for the function defined by f of x equals sine of 2x for the interval of x is an element of pi on 8 to 3 pi on 8. Okay, so what we need to do is our average, okay, is equal to our 1 on b minus a, integral of a to b, of our f of x dx. That's a rule that we've got to use. Okay, so that's equal to 1 over 3 pi on 8 minus pi on 8. Okay, from pi on 8 to 3 pi on 8. Okay, and our function is sine of 2x dx. Okay, so when we do this, well, we're going to be 1 on 3 pi on 8 minus pi on 8 is 2 pi on 8, or pi on 4. So we flip and multiply, so we end up with 4 on pi, okay, outside of our pi on 8 to 3 pi on 8, sine of 2x dx. Okay, which means we can say, well, we've got 4 on pi. Okay, when we integrate sine of 2x, we get negative a half cos of 2x, okay, from our pi on 8 to our 3 pi on 8. Okay, so when we do that, okay, we now need to sub in our values. So we've got negative a half cos of 2 times 3 pi on 8 minus negative a half cos of 2 times pi on 8. Hey, so what we get is we've got our 4 on pi times pi cos of 6 pi on 8, 8 is negative root 2 on 2, 8, and cos of pi on 8, of 2 times pi on 8, or pi on 4, gives us, well, we're going to be double negative, gives us plus a half times by positive root 2 on 2, okay, which means we've got double negatives cancel out, so we get 4 on pi times root 2 on 4 plus root 2 on 4, okay, which means we're going to be root 2 on 2 from here times our 4 pi, so we end up getting 2 root 2 on pi after a little bit of simplification. Okay. So I'll keep moving on. Okay, so there's also a little section on the total change as an integral of instantaneous change. So if we're given the equation for the rate of change, and we want to find the amount that's changed over a particular time period, we would integrate the rate of change equation using the starting and finishing times as terminals. So wet example 9, there's an awful lot of information in the actual question. Okay, so I didn't write it out. Okay, so this is one that you probably want to have a look at in your workbook too. Just the function is quite difficult to actually draw by hand. Okay, so the worked example is, it is common practice to include heating in concrete slabs when new residential homes or units are being constructed, because it is more economical than installing heating later. A typical reinforced concrete slab, 10 to 15 centimetres thick, has tubing installed on top of the reinforcement, then concrete is poured on top. When the system is complete, hot water runs through the tubing. The concrete slab absorbs the heat from the water and releases it into the area above. The number of litres per minute of water flowing through the tubing over 10 minutes can be modelled by the rule dV dt equals 2 outside of cos of pi t on 3 plus sine of pi t on 9 plus 3. Okay, and it shows you the graph of the function. Now that's the bit that I'm not going to draw because it's a composite function of adding these two together, and it looks quite odd. Okay, and it asks us for part A is what is the rate of water flow correct to two decimal places at 4 minutes and 8 minutes. So what we're going to do is sub 4 into this equation for t. Okay, pretty straightforward to do that. Okay, we're going to end up with cos of 4 pi on 3 plus sine of 4 pi on 9 plus 3, okay, all times by 2. Okay, correct to two decimal places. I'm not going to go through any of the working out. They don't really show much anyway. Is 6.97 litres, okay, per minute. Okay, at a time t equals 4. Okay, when we do the same thing with subbing in t equals 8, then it's 8 pi on 3 and 8 pi on 9. Again, when we do that, we get a value of 5.68 litres, okay, per minute. Okay, for part B, okay, we've got to state the period of the given function. Okay, so if we have a look, a complete cycle for the function occurs between t equals 6 and t equals 24, so the period ends up being 18 minutes. So really, we just need to have a look at our graph there, okay, and we see that we get to the same peak, okay, at 4 and at our 24, sorry, our 6 and our 24, okay, and so that's where we get our period from. Okay, so that's just reading off the graph. Okay, part C is find the volume of water that flows through the tubing during the time period for one whole cycle. Okay, so this is where we need to do our integration. So we need to integrate, well, our time period was from 6 to 24, okay, of our 2 outside of cos of pi t on 3 plus sine of pi t on 9 plus 3. Okay, well of course we can bring our 2 out the front. Okay, make it 2 outside of 6 to 24 of cos of our pi t on 3 plus sine of our pi t on 9. Okay, plus 3. So, and this should be dt. dt. Remember, not dx because our variable is t. Okay, so we get 2 outside of, well, the integral of cos of pi t on 3, well, it's 1 over pi on 3, so we flip that and make it 3 on pi. Cos goes to sine, okay, of pi t on 3. Okay, and then sine goes to negative cos. Again, we do 1 over pi on 9, which makes it 9 on pi cos of pi t on 9 plus 3t. Okay, and that's again from our 6 to our 24. Okay, so when we sub in our values, we can simplify things a little and say that we've got 3 on pi sine. When we sub in our 24, okay, then we really can simplify with our 3 to make it 8 pi. Okay, minus our 9 on pi cos of, we can simplify to 8 pi on 3, okay, plus 72, minus, go brackets around all this, minus our 3 on pi sine of 2 pi, minus 9 on pi cos of 2 pi on 3, okay, plus 18. Okay. So when we simplify all of that down, we end up getting inside here, okay, when we do our arithmetic there, we actually end up with 54. So we end up with 2 times 54, which is 108 litres of water has flowed through our pipes. Okay, so you'll just need to do the arithmetic to finish off there. Okay, we've got one last worked example to look at, which is worked example 10. Okay, which is about our kinematics. Okay, so we've got a particle starting from rest accelerates according to the rule A equals 3t times 2 minus t. Okay, we want to find a relationship between the velocity of the particle in v meters per second and the time. Okay, well, to get our velocity, well, velocity means that we find our integral of our acceleration. Okay, so our v of t and be our integral of 3t times 2 minus t dt. Okay, well, we'd expand out our brackets, okay, and make it 6t minus 3t squared dt, okay, which equals 3t squared minus t cubed, okay, plus c. Now we know, they tell us that particles starting from rest. Okay, so we know that when our time equals 0, initially, that our velocity equals 0. So when we put in t equals 0 and 0 on here, we find that c equals 0. So our v of t is simply our 3t squared minus t cubed. Okay. Part B is find the displacement of the particle after 4 seconds. Well, our displacement is our antiderivative of our velocity. So what we need to do is we need to integrate, okay, but we want to find the displacement of the particle after 4 seconds. Okay, so that means we need terminals on this. Okay, so our displacement x is going to be from 0 to 4, okay, because we want the displacement after 4 seconds, and it started at 0 seconds, okay, of 3t squared minus t cubed dt. Okay, well that's going to equal our t cubed minus t to the 4 on 4, from 4 to 0. Okay, well we've got then 4 cubed minus 4 to the 4 on 4. Okay, minus, well, put 0 in, it's all going to equal 0. And we can cancel out 4 here on the bottom, so it'd be 4 cubed minus 4 cubed. So it's actually going to be 0. So after 4 seconds, our displacement is actually 0 meters. Okay, so what that indicates is that we've probably gone forward, okay, turned around, and then we've come back, and after 4 seconds we're back at the initial starting point. Okay, part C is sketch graph of the velocity versus time for the first 4 seconds of the motion. Okay, I'm not going to worry about doing that. You can have a look at the quick graph in there at the moment, because I'm more worried about doing part D, which is calculate the distance travelled by the particle in the first 4 seconds. Okay, well, the problem that we've got, okay, with that is that if you look at your graph, you'll see that our area ends up partly below the x-axis, okay, and that we have an x-intercept at t, or a t-intercept if you like, at 3. Okay, so our distance then, we've got to split into 2 integrals from 0 to 3, okay, of our 3t squared minus t cubed dt, okay, minus 3 to 4 of our 3t squared minus t cubed dt, okay, because we need to be working with the area under our velocity time graph. That gives us our distance. Okay, so this is our velocity equation. Okay, so when we do that, okay, well, we're going to get, well, we know what our equation is going to be, okay, because we did it down here. Okay, so this time we're going to have, though, terminals, t cubed minus t to the 4 on 4 from 0 to 3, okay, plus and t cubed minus t to the 4 on 4 from 3 to 4. However, remember that this area is going to be negative. Okay, so what we're going to do is say, we're not going to add them, we're going to take them away. Okay, because we'll take away our negative, turn it into a positive. Okay, so when you sub in our values, we've got 3 cubed, take 3 to the 4 on 4, minus, it's going to be 0. Okay, when we put 0 in there, it's going to be 0. Minus 4 cubed, take 4 to the 4 on 4. Okay, minus our 3 squared, take 3 to the 4 on 4. Okay, when we do that, we simplify through, okay, we end up getting our first bracket equaling 54, our second bracket being 162 on 4. Okay, when we simplify both of those, which means our distance ends up being 13.5 metres. Okay, so that's all there is to this section. A few different application questions. As I've said in previous tutorials, application questions are really important to be able to get your head around. They're definitely going to be on Saxon exams, so make sure you practice these questions and get up to date and skill set ready for those assessment tasks.